Section 3.7, example 56, applying the comparison theorem. So use the comparison theorem to show that this integral diverges for all p less than 1. All right, so to prove that a function diverges, this time we have to look at a smaller function. Yeah, so we have to look for a smaller function in order for it to diverge. So we want p to be less than 1. So what we're going to do is find a p that's greater than 1 or equal to 1. So here, what we could state is that the integral from 1 to infinity of 1 over x dx, that this is less than or equal to the integral from 1 to infinity of 1 over x raised to p dx, for p being less than 1. So again, we want to prove that in order to prove that this diverges for p less than 1, we're going to find a value smaller that also diverges in order to prove that this one here diverges. So if the smaller one diverges whenever it's smaller than this value all the time, then this one's going to diverge due to the comparison test. So again, this is what we're going to prove to be divergent. Okay, so going from 1 to infinity, 1 over x dx. So this is going to be the limit as b approaches infinity, or positive infinity. So from 1 to b, 1 over x dx. The limit as b approaches infinity, ln of the absolute value of x evaluated from 1 to b. So what we have is a limit as b approaches infinity from ln of b minus ln of 1. Ln of b, or ln of infinity, goes to infinity. So this part goes to infinity and we're subtracting 0 from it. So it goes to infinity. So therefore the integral from 1 to infinity of 1 over x dx, this converges or diverges. This diverges to infinity, which therefore means that since the smaller one diverges, the larger one is also going to diverge because it's going to be bigger than that one. 1 over x to the p dx also diverges to infinity. So because the smaller one diverges, so does the larger one. And there we go. If you have any questions whatsoever, please do not hesitate to ask. Otherwise, bye.